In this session on bivariate analysis, we are particularly interested in finding the relationship between two dependent variables. Remember, in the previous sessions, I talked about dependent variable being dependent on many independent variables. Please note what I just said. I am interested in finding the relationship between two independent variables itself, right? If there is a relationship between two independent variables, I can predict one independent variable from another independent variable. Ideally, I don't want this kind of relationship among my variables as far as developing machine learning model is concerned, right? This is what is known as multicollinearity. That is, one independent variable can be predicted from another independent variable itself. Okay, so let's see all the techniques that are available in bivariate analysis. So bivariate analysis helps find the relationship between two variables, right? I know I said we are more interested in finding the relation between two independent variables, but bivariate analysis, broadly speaking, can be used to find out the relationship between any two variables, right? So we are looking at both association and disassociation, meaning there is a relationship, there is no relationship. There can be a positive relationship, there can be a negative relationship. Okay, all the possibilities are analyzed. Okay, and bivariate analysis can be performed for any kind of combination of variables. That is, one variable could be continuous, another variable could be categorical, right? Both the variables could be categorical, both the variables could be continuous. There are different types of techniques for different types of combinations. We are going to see all of them in this session. Okay, we will first start with the relationship between two continuous variables, that is two numbers, so to speak. Remember, I gave the example, right? Number of marks obtained and the number of hours I studied, right? That is an example, right? Here, the primary technique that we will be looking at is what is known as a scatterplot. Okay, it graphically shows whether there is any relationship between two variables, right? You can visually see. As I mentioned, it can be a positive, it can be a negative relationship. There can be a relationship, there need not be a relationship, and the relationship can be a linear, which means a straight line can be fitted. Okay, what is called as a line of best fit. Okay, um, or it can be a non-linear relationship, like a polynomial kind of a relationship. Okay, or a logistic relationship also. So scatter plot shows the relationship between two variables, right? But it doesn't tell the strength of the relationship. Okay, so for this we use what is known as coefficient of correlation, right? It derives from the scatter plot, because in scatter plot we fit what is known as the line of best fit. Okay, using the line of best fit you can find out what is the extent of correlation between two continuous variables, right? For this, as I said, we use coefficient of correlation. So correlation varies between -1 and +1. Okay, -1 indicates perfect negative correlation, +1 indicates positive linear correlation, and 0 indicates no correlation. This is -1. Okay. The point is, many times, you won't get this -1, +1 and all. You will get values that are closer to 1, right? So which means, if it is 0.96, it is closer to -1. So it means it's a nearly a perfect linear correlation. You can even get a value of say 0.6. That means positive correlation to some extent is there. So those are the judgments, you need to make based on the coefficient of correlation values, right? So this is the scatter plot, right? In this example, I have drawn the scatter plot for relationship between applicant income and loan amount. Remember, these are two dependent variables, right? We can find that there is no relation between the two, right? In the other scenario, the applicant income, co-applicant income, that is also being compared, but see the scatter plot, it is scattered all around, right? Quite literally, it is scattered all around. That means there is no relationship, right? You can plot this whenever you have two variables and you want to find the relationship. Immediately plot a scatter plot, right? A very, very simple tool to ascertain the relationship between any two variables. And you can visually see if there is any relationship or not, right? You can also see, is it a case of linear relation or is it a case of polynomial or other types of relationship. All those things can be seen here, using this scatter plot, right? And as I discussed earlier, I use coefficient of correlation, right? That is the extent of correlation that is there. The numerical measure of correlation is the correlation coefficient, right? In this case, we have taken applicant income and loan amount, right? We are getting a correlation coefficient of 0.56, right? Which means there is a moderate relationship, right? Moderate positive relationship. Between applicant income and co-applicant income, it is a negative correlation, but it is a weak correlation. Please understand, this is closer to 0, right, than to -1 or +1. If you look at the relationship between applicant income and loan term, it is in fact closer to 0, right, -0.04. That means there is a weak relationship between two variables. Are you getting what I'm trying to say, right? Scatter plot helps you to visually see the relationship, right? Whether there is a relationship or not. Coefficient of correlation gives us a numerical measure to find out the extent of correlation that is there between two variables. I can use this concept to determine whether there is any relationship and decide my course of action. Okay. What is that course of action? Ideally, I don't want correlation between two independent variables. I will remove such variables, right? So that is the primary action. Now, the other type is categorical and categorical, right? If the two variables are, both of them are categorical in nature, we use what is known as a chi-square test, right? It is used to derive the statistical significance of relationship between two categorical variables, right? It is based on the difference between expected and observed frequencies in one or more categories, right? The categorical, it can have multiple levels of categories, right? We create what is known as a two-way table, expected and observed frequencies, right? It basically returns a probability for the chi-square distribution, right? Basically returns a probability. If the probability is 0, right, it means that both the categorical variables, right, are dependent. Probability of 1, it shows both are independent, right? So that's closer to 0, closer to 1. But we are looking at 95% confidence level, which means that we will take a p-value of 0.05, probability value of 0.05. If it is less than 0.05, it means that there is a relationship between variables, right? Please note, this is what we will be using for finding out the relationship between two categorical variables. Okay, chi-square test is what we are going to use. Clear? To understand this, okay, because we will be using the concept of hypothesis testing, right? If you recollect, we talked about dependent variable and an independent variable, right? High school mathematics concept. This is also something that we learned in our high school and probably college days, right? So hypothesis testing is a concept where I'm trying to derive an inference about a population based on the information I have about sample. Remember, the population was a sample concept that we discussed in the earlier session, right? I am doing an opinion poll by taking feedback from some of the electorates, right? From some of the people who are eligible to vote, right? I'm not going and taking feedback from all of the people who are eligible to vote. I'm only taking feedback from some of the people. and hence I am inferring that a particular party is expected to win the elections, right? So how can I conclude that the responses of few people are good enough to determine the outcome of an election where more people are involved, right? So that is where the concept of hypothesis testing comes. I am trying to draw inference about a sample based on the performance. I'm trying to draw an inference of the population based on the results of a sample, right? Based on a sample, I infer about the entire population. For this, I am making use of the concept of hypothesis testing, right? So if you see the photo that is there, I apply fertilizer and the plant grows, right? So what is the hypothesis? The hypothesis is application of fertilizer increases plant growth, right? So that is stated as an alternate hypothesis. Alternate hypothesis is what we want to prove, right? What we don't want to prove is stated as a null hypothesis. Application of fertilizer does not increase plant growth, right? There is no impact, right? So alternate hypothesis is what we are trying to prove, and null hypothesis is the opposite of that, right? We actually don't try to prove a hypothesis, rather we try to either accept or reject the alternate hypothesis. So that is the way the concept of hypothesis testing works, right? So in our case, the alternate hypothesis will be there is a relationship between two variables h0. There is no relationship between two variables, right? If the p-value is less than 0.05, we accept that, we conclude rather there is relationship between two variables. Is this clear? Is this clear to everyone? Right? So let's see some examples. Here I am taking two variables, right? The education level and the whether the individual is self-employed or not. It's an yes/no kind of scenario, right? So please note that if there are more than two levels also, you can still use chi-square, not just when I have two levels like education, graduate or not a graduate, self-employed, yes or no, right? If I have a variable in which more than two options are there, then also chi-square test can be used. Okay. Although the example that I show here, there are only two possible outcomes for each of the variables, right? Two possible levels. Here, the alternate hypothesis is education and self-employed are not independent. Look at the way I am structuring this. I'm saying they are dependent, right? So I'm essentially saying they are not dependent, right? The null hypothesis is they are independent of one another. There is no relationship, right? And the chi-square value that I'm getting here, okay, is 0.0236, but I am more interested in the p-value, right? That is what I'm interested. So the p-value is 0.8778, right? That means the p-value is greater than 0.05. That means, we are accepting the null hypothesis. That means there is no relationship, right? In the case of, let's see one more example, education and property area, right? So here also, the p-value is turning out to be greater than 0.05. That means there is no relationship between these two variables, right? So whenever we have two categorical variables, right, we use the concept of chi-square, right? The primary metric that we are looking at is the p-value, right? Which is if it is greater than 0.05, we can conclude that there is no relationship between the two variables, right? So for this, we are using the concept of hypothesis testing, which I explained a little earlier in this session. Clear? Now we are going to look at the relationship between categorical and continuous, right? So for this, we are going to use z-test, t-test or ANOVA, right? Again, these are coming from statistical concepts, right? ANOVA comes whenever we are looking at more than two groups, right? If there are more than two groups, right? Whereas if we are only looking at comparing two groups, we use z-test or a t-test. Both are in fact similar, okay, but t-test is used whenever the number of observations, okay, is less than 30, right? So obviously in most of the cases the number of observations, the number of data, the number of historical data that we are taking up for building the machine learning model will be more than 30, so invariably we'll be going for t-test, right? So what do I mean by two groups, right? Which is what, the categorical and continuous, right? I have two variables. If I want to compare more than two, we are looking at ANOVA, right? The examples that we are going to see are only two, right? But if you have more than two, you can definitely use ANOVA, right? So here also we are going to primarily look at the p-value, right? It is a p-value that is of importance to us. In this case, we are looking at if there is any relationship between applicant income and loan status, right? This is, look at this, we are computing the z, right? And we are using the z-test, right? And we are computing the probability that is involved, right? Here also we are stating the null hypothesis and alternate hypothesis. Alternate hypothesis, there is relationship. Null, there is no relationship. The p-value comes out to be greater than 0.05. In fact, it is closer to 1, right? We can very well not reject the null hypothesis. So remember the way I am stating, this is the way the world of hypothesis testing works, right? I either accept or reject the null hypothesis, right? Which is, there is no relationship, right? Here I do not reject, okay, which means I accept whatever null hypothesis states, right? But if you want to understand it simply, not bother about null or alternate hypothesis, right? If this is confusing to you, just look at the p-value. Just see if it is p-value is less than or greater than 0.05. If it is greater than 0.05, there is no relation. Okay, nothing to worry. If it is less than 0.05, there is relation and you need to worry. And the course of action is you remove the variable, right? That is involved in the relationship, right? When there is a relationship between two independent variables, you want to ideally remove one of them, right? So that's a call you take, right? So a concept that is related to this is what is known as multicollinearity, right? Can I predict an independent variable from another independent variable, right? So, it is like, for example, can I predict the co-applicant income based on the applicant's income itself, right? If such a relationship exists, it is definitely a big cause for concern. In the previous we saw there is a relationship, but here I'm going one step further, right? I'm checking if an independent variable can be predicted from another independent variable. This is known as multicollinearity. For this, we'll be using the concept of variance inflation factor or VIF. And if you use this preloaded library that comes with Python, right, you can find out variance inflation factor in a jiffy, right? So see the variance inflation factor for each of the independent variables. There are some variables where it is higher, like 6, 10, right? Many other variables, it is not so high. So obviously our interest level is higher where the VIF is higher, right? Anything beyond 5 is a cause for concern, but if it is greater than 10, you must remove the multicollinearity, right? Remove some of the highly correlated independent variables. So which is 10? Loan amount term, right? Multicollinearity, remove that, right? You can also combine independent variables, such as you can add them together. You can add, let's say, for example, the applicant income and co-applicant income, right? That is one way of looking at it. Or you can perform an analysis that is meant for highly correlated variables, such as PCA, principal component analysis, or partial least square regression, right? Those are techniques you can adopt, but the one that I have found best uses, remove them, right? Take a call and remove them, or you can add them together, right? These two have worked very well. So what is the primary action that you will be taking if there is multicollinearity? That is, if VIF is greater than 10, remove them, right? So this is a key thing. And I also don't want too highly correlated variables, right? We saw through chi-square regression, right, which is the scatter plot, and z-test and t-test, right? That also indicates there is a relationship between the two variables. I don't want any relationship, right? Especially a positive relationship between two independent variables, right? So I don't want such variables, in my data set, because they will definitely pull down my forecast accuracy. Clear? So that's what I wanted to cover in this session. We will be seeing how to handle missing values, what actions you need to be taking in the next session. Okay.